Hi everybody, welcome back from coffee break. So next we're going to hear from John Elliott, who's here at Leeds, and he's done a lot of work on earthquake deformation modeling, intraseismic, coseismic, seismic cycle, and he's going to be not only lecturing a little bit on earthquake modeling, deformation modeling, but then he'll also be leading the first bit of the practical when we go upstairs after the lecture. So
thanks, Jonathan. So this leads on from what Pablo was speaking about this morning. So I'll return to a couple of the issues that he brought up about using these data sets, but applied specifically to earthquake modeling. And I'll start with what we call the forward problem. So the easier bit, I do the easier bit, and then Fabian this afternoon will do the harder bit, where you do the inverse modeling side of things. So we'll start with the easier bit. So I'll go over the coseismic part of the earthquake cycle, the deformation, how we apply the elastic dislocation theory to measure what's happened in that earthquake, to derive the fault parameters after. I'll also say why we sort of want to do this in terms of interpreting the geology or the rheology of the Earth's crust and its link to the seismic cycle. And then I'll just introduce the two earthquake examples that you'll do the forward modeling for on the computer labs upstairs. So this will be about 45 minutes to an hour before we spend the rest of the remaining time upstairs. So as with any sort of science discipline, you start with the observables. So an observational science, it's what we can measure. So you've all been doing this week, the satellite InSAR measurements. This is the Cheekstone earthquake here from a few years ago. But that can be augmented with GPS data very readily and seismometry. As long as you have the framework of how you're going to model those, you can combine those to make up for some of the strengths and deficits of each of these techniques. But we start with the observations. Now we do that so that we can model the phenomena that we're interested in this case, earthquake slip. So using the sort of forward models and the inverse processes, we can get at what perhaps is the nature of slip at depth beneath the fault trace, and potentially corroborate that with what geologists may observe at the surface in terms of the actual fault offset that's measured. Because there are many limitations with modeling, it's very hard to get the truth out of these things. You'll see that you can actually play around with the parameters and get roughly the same result. So it's always good to have as much ground truth as you can. Don't always believe in models. It's very easy to come up with pretty pictures that don't have any bearing on reality. But the whole purpose of doing this workflow is to also get at the kind of interpretation. We want to understand the growth perhaps of geological structures, faults and folds, the interaction between them, how you propagate folding, or to look at seismic hazard from a sort of stress point of view. So those kinds of list of things, as I said, looking at maybe the growth of anticlines, how fault slip rates through time. You've got comparing what the coseismic offset is to the longer term interseismic rates that might be measured with InSAR GPS. How is the cross deformation distributed? Okay, do you have a lot of single major fault, or is there a lot of off-fault deformation? What can we infer about the nature of faulting at depth? I mean, we're imaging with InSAR here, we're inferring what's going on 10 kilometers beneath the Earth's surface. What does that mean about the state of the rheology? Where is the cross brittle? Where is it behaving perhaps aseismically with creep? And combining that with the earthquake cycle, the links with post-seismic deformation we might see from the stress perturbations from the earthquake. You need that starting model to be able to move on to any other sort of assessment of the afterstep. And then perhaps probe with that some of the rheological parameters, maybe about fault friction, about the nature of the rate and state friction you get on faults, or perhaps getting at parameters such as the viscoelasticity you might see in the post-seismic. You would need a good co-seismic driving model to start with. But there's also the sort of human perspective on this as well, measuring these earthquakes. One of the driving forces is the earthquake hazard. There are many densely populated areas, say in India and China, exposed to such hazards. This is the distribution of earthquakes that have killed quite large numbers of people in the last 100 years. We're often surprised by exactly where these faults are. InSAR gives you really quite a good location on the fault, whereas in the past, seismology could have been out by many tens of kilometers in rather remote parts of the world. So we look at the sort of recurrence, and we study these events wherever they are on the Earth to be able to try and understand perhaps more local phenomena. Because of the long recurrence, you can't wait for a given fault to go, but you try and apply your understanding from elsewhere in the world to similar strike slip zone in China could then be informative of what's going on in Turkey, and enable you to interpret the long-term geomorphology, what we see in the fault offsets with the InSAR today and the models that we generate. How does that compare to what a quaternion geologist would record in the offsets seen at the surface? And ultimately, one of InSAR's goal is to look at the longer term strain, the instatic strain rates, to really pinpoint not a prediction of where these earthquakes are going to be, we can never do that really, but a forecasting of where the strain in the crust is building up, so you can hone in on the places that you want to reinforce structures to increase the resilience of your population. So just to bring that home, one earthquake I worked on in the past with colleagues at Newcastle was the Yushu event. This was the city before the earthquake. This was a magnitude, not quite a magnitude 7, and it caused almost total destruction of this city, killing a large number of people and about a quarter of the exposed population there, because the building structures are not resilient enough to withstand it. So that's the two sort of driving mechanisms, the science and the physical understanding and the societal impacts that we want to do. And seismology for the past 100 years has given a lot of insight into that, and also understanding plate tectonics. But in the past sort of 20 to 25 years now, there's been an increasing number of earthquakes that have been studied with InSAR across the globe. And since the launch of Sentinel-1, we've been able to look at really most of the shallow continental earthquakes that have struck in the past few years. This sort of obviously started with the Landers earthquake in 1992, this early Nature paper, but we've worked on quite a few spread across the globe, from shallow continents to actually subduction zones, looking at only the onshore portion of it, but this is the Tohoku earthquake where you can see the deformation. So you're very familiar with these sort of fringes now. And the kind of events we're looking at, this is just the magnitude range here. We can sort of measure the things above about 5.5 or 6. Obviously, the big events, everyone well recognizes, big earthquakes dominate the energy release in these. If you want to understand the sort of energy budget, you look at the big things. But in trying to interpret what's going on, you can learn a lot also from looking at these small earthquakes. They highlight various active fault systems or the distribution of deformation that you might want to understand in your rheological modeling. And the number of events that we're sort of looking at here is in this range. If we look at magnitude 8.5 to 9.5, there's about 0.16 per year. So we're looking at 7.5 to 8, there's about 1 per year that's going to affect the continent. So that's measuring these big ones with these sort of inside data sets it's only once per year, but that's the kind of response we normally do. It goes into many tens though, if you're looking at smaller ones. These are the onshore ones. There's obviously a lot more offshore earthquakes for which InSAR is totally useless. Now there's a depth magnitude trade-off. You can't look at these really small fracking ones of 0.8 that are happening in northern England at the moment. The surface deformation just wouldn't be large enough. So this is the contour bands for a fringe, 2.8 and 5.6 centimeters for the magnitude and depth. So obviously a big earthquake, whether it's at the surface or deep, you're going to see enough deformation at the surface that InSAR is going to be a useful tool. But you can only really measure magnitude 5.5 if they're really quite shallow. So there's this trade-off, a cut-off with what we can get at. And it depends on whether you're ascending or descending and what kind of faulting style it is, the exact amount of deformation you get at the surface, but that's the sort of rule of thumb. And there is still a chance, an opportunistic chance to go for really quite small events. They don't necessarily have to have been seismic, but if it's a very shallow event, you could actually get at really quite small earthquakes. This was a study done quite a few years ago, but they were getting below 5.5. If there's been a significant aseismic slip at the surface, you might also see that. So it's not a hard and fast rule. You might want to be opportunistic, and that's part of COMET's goal, is to be able to measure the deformation everywhere, to be able to pick up maybe some of these silent events that are happening in particularly rheologically weak zones, such as in this case in Iran in the Zagros. So just to recap, you should have seen various animations of this. We all like to make different versions of this, but the principle for the earthquake deformation, it's quite large amounts of slip that we're getting, so you're expecting to see really quite a few contours. This is normal faulting. We get lots of InSAR fringes, contours of slip that vary spatially. And that's the principle you're going to be using here, looking at both line of sight deformation that's linked with either uplift or subsidence or lateral motion on the fault. That's what we're after. It may be buried, it may breach the surface, so you might get discontinuity in the face, but you'll see some examples of that. But the guiding principle with this is that with just a single look direction, you're happy with the line of sight. There is a huge ambiguity when you then run these models about what's gone on. Don't know whether you can see this on the screens, but when there is a line of sight change, this could either be synonymous with vertical uplift, purely horizontal, or some motion in the line of sight. There's always that ambiguity. That's why we prefer to have at least 2 look directions to be able to do this modeling. So there are huge trade-offs if you do this modeling. That's why it becomes quite hard to measure some of the parameters such as the fault rate, because it can trade off hugely with your lack of sensitivity in the data. It's not the same as, say, having a really dense network of 3-component GPS that give you the total sort of displacement. And so always keep that in mind about that ambiguity. And you're happy with the sort of counting, I think, of fringes now. You're looking for a far field 0 sort of point. This is the Haiti earthquake that killed almost 250,000 people that happened outside of the city. And it's an exercise when you unwrap these of counting the contours. You're going to be comparing this afternoon probably both fringes, wrapped and unwrapped data. But you want to get a gut feeling of, is it a reasonable amount of motion you're getting, and in your mind knowing which motion is towards the satellite and which motion is away. So in this case, this is 60 centimeters towards the satellite, and you could just make out this lobe here that's 12 centimeters away. So this was along this fault that was actually buried because the fringes don't meet discontinuity, buried outside the city, and the rupture headed towards the city. That's why it had such a big impact. Another example was recently is a reverse faulting earthquake, Pishan, at the Italian Basin. So now with the Sentinel data, it's very clean, good looking stuff. There's the uplift and the subsidence lobes that you often get. You're looking for 2 or 3 lobes, often with these sort of events. You get your eye in on these things, and then you unwrap it, and that gives you the sort of 5 centimeters of motion up and a few centimeters away. So this is the 0 point here. There's often an ambiguity about which way the fault dips. It's very hard to measure these when the fault doesn't actually come to the surface. Here are your patches of incoherence in the Tarian Turkmen desert, these sort of sand dunes that are moving, and various unwrapping errors that you get over the mountains that can be quite difficult. So I'm just going to step you through the processing steps that you did probably on Monday now for the Nepal earthquake, just to show you from start to finish and remind you the steps that were happening behind the scenes when you ran these codes. This is your multiple bursts of an SLC over Nepal. Kathmandu is here. See the mountains here with the foreshortening and the shadowing that you get in the very high Himalayas. So it's a big problem when you've got a lot of mountains. City there, and then the Indian Basin down there. You've got your various 3 swaths, 1, 2, and 3. Okay, and that's how the data sort of comes. You run all those routines that you were doing that will stitch that together into a single mosaic. It might be a multi-looked intensity image. Also, maybe you see lovely mountains there, flat sedimentary basin in India here, and Kathmandu there. We now zoom in on just a portion of that's made up about 5 for the bursts. The initial interferogram you get from the before and after date looks something like this. It still has a lot of orbital errors, particularly in the early days when we were doing this. This is work I did with Pablo Gonzalez, who spoke to you earlier. We had lots of problems with the orbits. They've got a lot better, but you get a lot of fringes in here, and hopefully you can see the discontinuity here. You remember you're doing lots of azimuth refinements, and the code does this in the sort of background. But it basically, each time you try and refine the offsets for the burst, this is hopefully very familiar to you, you get a slightly better matching and you lose these discontinuities. You do that multiple times, and basically what the code is doing is shifting one of the images with respect to the master just by small fractions of a pixel until you're getting below a certain threshold where you lose that. So that was all discussed Monday and this morning. Everyone should be very happy with that. This is just working this through for this particular event. You then go on to the next step. Hopefully you can see this is small amount of deformation. Everyone can see on the screen, hopefully, a lot of fringes out here. The next sort of steps you do to try and pull out the signal a bit more is the phase filtering. So again, that can be done iteratively. You do it a few times. And it's really pulling out the signal. There is a cost to doing this. The harder you filter it, the more you'll smear some of the high fringes, and you will get unwrapping errors when you do this. You can see that you might get some artifacts here as you blur things across, but it makes it a bit clearer, and at some point can make the unwrapping a bit easier, but you'd be pretty wary in here about all the mess that's going on. This is also C-band, Sentinel, also the L-band did a lot better up here in the mountains with the longer wavelength, because it didn't have such a problem with the fringe rates. You can really see you're aliasing here and losing those fringes. So that's your nice, cleaner earthquake deformation interferogram then. That's in the radar coordinates, so it's the sort of wrong way around. You then do the geocoding step. This is the coherence, not very clear on, this is sorry, the coherence, that's the intensity image. This is the coherence showing the low and higher coherence here around the city, and then low back in the mountains. East is now properly over there, west is over here. That's that interferogram now properly geocoded. And then you can also put a different rewrapping. So this is original wrapped at the standard C-band contour interval. You can rewrap it. That's a good way to look for unwrapping errors in here. You can perhaps see a few in there that we had. So this is now wrapped 10 centimeters. Again, makes the deformation a bit clear. And then you do a full unwrap to get the total displacement, which was a couple of meters up here. So you've done all those steps. This is just for a very big event. This is in the early days when we had to do it piecemeal. You can actually stitch these together to get the full deformation. So I'll just go on now to, I don't actually know the complete background. Half of you, I'm sure, are very familiar with earthquakes. I don't know whether the other half are quite so familiar. So what we're doing when we're looking at these fault and earthquake parameters. So how big an earthquake is, we look at the moment release, that's measured in Newton meters. We need to know how big the fault is, so how long it is, how wide it is. These are the kind of key characteristics we're trying to learn from the INSAR. The INSAR is very good at these sort of spatial dimensions, as long as it's not too deep. And the amount of slip, that's what we're after, the slip at depth. Now, combining all those fault parameters together, you can actually get the energy release for the earthquake. It's given by this equation, which needs to relate the rigidity as your sort of term that then gives you that energy. The rigidity will vary with depth and get large, but that's the typical value we use for shallow crumbs. That'll tell you how big it is, and you can convert that into a moment magnitude as well. You can use rules of thumb for a lot of these. If you want to look at the scaling relationships, there's a compilation of from Wells and Cosmos and increasing with INSAR, we can do the same thing of the sort of characteristics of if a fault is a certain length, it's capable of a certain amount of slip. And that's the sort of ratio you get, 5 times 10 to the minus 5, but easy being sciences and geology varies by an order of magnitude. You can also, rule of thumb for smaller earthquakes is you can say they're equidimensional. These are what we used in the past. Actually, what I increasingly find, and I'll show you quite a few examples, is that even small earthquakes tend to break this down. You get long, thin ruptures. But it's only for larger earthquakes. We always used to think that it would rupture the whole seismogenic crust, so many areas, that's 15 kilometers. Again, that kind of, the more INSAR results we've had, the more that kind of rule of thumb is starting to break down. But that's that conversion into the moment magnitude, so the kind of MW that you're used to for how big the earthquake is. So the INSAR is very good giving you the physical dimensions, giving you what is the geodetic moment. Now you've got to remember, because you're taking an image many, perhaps days after an earthquake, it will be contaminated with post-seismic. So it doesn't necessarily have to match the seismic moment though. There would be an expectation to have some discrepancy depending on how much aseismic, post-seismic motion there is in your interferogram. If your second slave image was acquired just after the earthquake, then you'd be pretty sure that's predominantly co-seismic. But even with the regular acquisitions we have today, that's not always true. It might be many days. Also, for those of you not quite so familiar with the types of faulting, it's going to be key for doing this practical class is understanding what these fault parameters are. Who actually knows all about strike slip, dip slip, reverse faults, normal faults? Just so I know who I'm preaching to. Yeah, so it's about half of you. Okay. So lateral motion, strike slip motion. This is the distribution of earthquakes. That's usually at transform faults in the oceans, onshore major strike slip faults such as in North Anatolian Fault or the Altan Fault in China. This is the kind of focal mechanism. It basically means that slip happens laterally like that. Normal faults, that's where you drop down one side quite a lot, get a lot of substance and a bit of hanging wall uplift. Okay, so this drops down a lot, this goes up. InSAR's really good at measuring that because it's mainly looking down. And the reverse of that is reverse faulting or thrust faulting if it's at low angles. This is the typical subduction zones that you get, or at the edge of the Himalayas, that Gorkha earthquake I showed you before. So that's the whole suite of them. You can see oceans very well delineated, that's your plate tectonics, continents very diffuse deformation. And brilliant for InSAR, that's where we spend most of our time looking. So just to hit home, I'll do this twice now and at the end. You're looking to give us, through your forward modelling, the strike for the fault, so in which direction is the fault along strike, dip down to the right, so the angle from the horizontal down, and the slip vector gives you the rate direction. Okay, so these are sort of three of the key parameters to do with the fault slip and the fault orientation. We'll go through that a bit more in the practical a bit later. So just remember the rate's the most complicated one that we're talking about is the slip vector relative to the strike direction. Down motion, normal is negative, up motion is positive, and it goes -90 for normal, +90 for reverse, 0 degrees for left lateral, 180 degrees for right lateral. What we don't get from the InSAR are these sort of things. The hypercentral, the focus, that's where the rupture started. InSAR can't tell you anything about that. Can't tell you so much about the epicenter either, of where that has to come from seismology, because that's all to do with time. Centroid depth, you can get that from seismology and from the sort of InSAR. That means that where was the average energy, the moment released from. Can't get at the source time function or the seismic moment, but we can get that geodetic moment. So you have to be careful if you're comparing apples and oranges when you try and corroborate this with other observations. There's also quite a suite of data that you can get out of the InSAR techniques. We're going to show you this as an example of a Burma earthquake. The conventional InSAR, that's what you're mainly doing. You can move these on a bit as you become technically more proficient to exploit these data sets, particularly when there are large displacements. Taking the range offsets here, so this is actually pixel tracking more the amplitude now, not looking at the phase component. So this was, you can see now very clearly where you'd want to put the fault here and here. This is an example from DARPA that really helps pin where the discontinuity is. It's often useful because we lose those fringes, the very high fringe rate in the near field or from excessive shaking that reduces the coherence that you get. But you can get the range offsets, the azimuth offsets as well. So that's just a long track rather than the range displacement. And MIA, multiple aperture InSAR as well, for looking at backwards and forwards portions by splitting the band. So these are much more complicated techniques that we've not really shown you here, I think. But you can get at this with many of the data sets. And one thing I was trying to emphasize with the different strike slip, dip slip faulting that you get really quite a plethora of deformation patterns. So people have tried to sort of throw machine learning at this to try and say, can you pattern match this? This is obviously something you'd want a pattern matching algorithm to be able to do. It is a bit hard. You'll see when you do the forward modeling, you can get it relatively quickly, but they come in such variations, you can't throw enough real world examples at it, and you get quite a bit of complex faulting. But this is a strike slip fault where it's an east-west striking fault, and this is a strike slip fault where the fault is north-south. So there's similar phenomena, just slightly orientated differently with respect to the satellite, gives you quite a different pattern. This is another strike slip earthquake that's ruptured right through to the surface. That's the Burma one, that's why it's broken. These are buried reverse faulting. So you get really quite a different display of the fringe pattern. And that's why you need to sort of do the modeling to understand exactly what has gone on in these events. There's also a couple other things that Bobby pointed out this morning that you have to include with the modeling, not just the phase measurements, but you need some ancillary data to go with it. And that's to tells you about the orientation of the satellite with respect to the ground. This is a hill-shaded DM of the Iran-Iraq border, with the Zagros here. Where's the earthquake in here? This is the phase measurements that have been unwrapped. Where's the earthquake? Shout out. Earthquake detection, people. Somebody shout at the mayor. The blue dot. Okay, that's the earthquake. That's atmospheric noise over the Mesopotamian basin. That's the earthquake just there. You've actually got 8 centimeters of motion towards the satellite. We'll call it negative in this case. and there's a slight hint of a load there. The rest of it's noise. Here you can see an interference pattern from probably the atmospheric convection cells on the before and after imagery. That's our unwrapped data. You can see that these small earthquakes are easily lost in the noise. It does help to know that from the seismology there's already an event there. But the thing you also have to include as metadata is the incidence angle. So this is on an ascending path, right-looking sentinel. So the incidence angle, which remember is slightly different from the satellite look direction, is the angle at which the radar intersects the Earth from the vertical. So in the near field, this is near range, that's 31 degrees. So it's relatively steep, that means. In the far range, it's at 45 degrees. So the satellite incidence angle with the ground, satellite looking down that way in here, and it's looking more up that way. Now remember, because the Earth is curved, there's a difference between the incidence at which it hits the ground and actually the angle at which the satellite looks. So that can be quite easy. Make sure you know what you're throwing into your code and what you're getting out of your processing toolbox, which way around it is. There's also the azimuth direction. So this is going northwards. So it's about 349 degrees here, 351. There's not much variation in what counts with respect to the Earth, its azimuth direction. But you have to include this in the modeling. It needs to know what the look, the incidence angle and the azimuth is. Obviously, if you go in this is about 30 degrees north. As soon as you get to high latitudes, you could be going equivalent almost westwards on this. It's just your local azimuth direction will vary quite a lot because it's a polar orbit that has an inclination that's not 90 degrees, so it won't go right over the poles, it will go just to the side of the poles. So that will vary with latitude quite a lot. And compounding those two things, you get really quite, for the same event, these are forward models, like you'll be doing, forward models, depending whether you're descending or ascending, whether you're looking to the right or the left, most of the satellites look to the right. Most of them don't turn, you get really quite a different pattern. Now this is good and bad. It makes it hard to interpret straight away, but it means if you have multiple look directions, you have more information about what's going on in the earthquake. So having more look directions, more data from different perspectives, getting a different view on the earthquake is always better. And you can then break this line of sight deformation if you have enough information or a good enough model into east, north, and up components. So you're breaking it, decomposing it into that three components. That's an example that Tim did in the early days from Alaska. So what do we do with that data to get the model we want? Well, we put it through the theory of elastic dislocation. So really quite a long-standing theory about how you just cause a break in the Earth's crust. And if you imagine that was an elastic medium, the deformation you get from a discontinuity, a buried discontinuity at the surface. And if you do that and you say, I've got a discontinuity here through here, it's a fault, but it's discontinuity, how you expect the crust to bend, to warp, the dislocation, how the strain is spatially distributed is just given by this profile here. Okay, so near the fault, where the fault has slipped, you get discontinuity, quite a large displacement, and then it dies off to the far field, sort of zero. That's what we're doing in all these events. If it's dip slip, the phenomena you'll get for a dip slip is you tend to get a large amount, in this case this is substance, no this is, sorry, reverse faulting, so this is uplift, and then only a little bit here of substance. So there's an asymmetry, and that it's not as symmetrical as for a strike slip fault, dip slips. You get a lot more uplift for reverse faults and a lot more substance for normal faults. So this is a normal faulting earthquake here from Dinar. Huge number of fringes in what will be the hanging wall, just a couple of fringes of uplift in the footwall. So with enough sort of playing with these, you get your eye in for this. As long as you know which way around, if it's a normal fault, you know this must be the hanging wall substance that creates basins. This is the footwall uplift that creates the mountain. So to do this, many of us rely on an Okada formulation from the mid-80s to describe what happens on the fault. Depending on how the modeling is set up, it depends what reference frame you're in. In this paper, it's done in reference to the fault itself, as opposed to in a sort of geodetic framework. But you've got the position of the fault and the depth of the fault plane, its dip, its width, its length, all those parameters that InSAR is very good at getting at. And then you have the strike slip and dip slip components U1, U2 that add together to give you the slip vector, the total slip vector with a certain amount of rate. You can also, in a medium, for dikes that you'll do this afternoon, probably have an opening. That's the tensile component as well. That it can be solved for when you think that you might have, say, normal faulting above the dike that's extending, something like that. When you do this, we actually convert this into having a stripe, dip, rake, and a location and of the fault, but it's basically the same number of parameters, about 9 parameters you're trying to solve for in one go. And it was mentioned this morning the various methods of downsampling this. I'll just show you from a particular earthquake in Tajikistan that this sort of downsampling that's important. The InSAR has obviously millions and millions of data points. You certainly can't do an inverse problem with that many millions of points, and it's also a bit slow to do a forward problem with that many points, so you downsample it. So here you've got nice 5 kilometer patches of in the far field where you expect it to be 0. You don't want too much data telling you it's 0, but then you sort of can nest in some way. You nest and hone in on where you expect really quite large magnitude slip to have many, many data points. So that sort of principle. We just have to be very careful about how you do that. That will obviously bias it quite a bit to the near field, which is often what you want. And there's various theories that Pablo showed you for trying to find the best way to do this. I keep it really simple. I just do nested uniform slip, but there are many more reasonable ways of doing it, more complicated, that you could justify doing. This was a relatively four-strike slip fault, but you can see it's made up of a few segments on the data, and actually that's what InSAR is really great at giving you. This is the Darfield Christchurch sequence from 2010-11. The aftershock cloud gives you quite a hint at really quite how messy this earthquake was, but the InSAR really pulls out where the fault segments are going to be. Where you lose coherence, you actually get 10 segments out of this model or so. Really quite a complicated earthquake for magnitude 7.1. But this really is why the kit is very powerful, something you really can't get at as easily with seismology. You wouldn't have been able to build up a 10-fault model that you would reasonably believe in the same way. And then a few months later, the Christchurch earthquake happened on something that actually mirrors the Darfield at a smaller scale, but had a much greater impact because it was right beneath the city. So not only do we want to look at a long strike segmentation of faults to understand how the crust breaks up, one of my interests is trying to understand how does it break up at depth. So here's 2 examples I'll return to. They're both the same sized earthquake, okay? They happened about a year apart, but you see in this one, you've only got a couple of fringes. There's not much deformation. And in this one, you've got a lot of fringes. So the take-home message, if they're the same seismic moment, but you're seeing a vastly different amount of fringes, so pretty much exactly the same part of the mountain range, it means that this one must have been a lot deeper. If you put your source deeper, the amount of deformation you see at the surface is a lot less. Whereas if your source is nearer the surface, you're going to get a lot more fringes, even if it's the same energy release, the same geodetic moment. So in this case, we were looking at the fault being a lot shallower about a year later compared to the one that happened before. One of the difficulties in trying to do this is that ambiguity, though, of these faulting. I was discussing this with a colleague just earlier, that you can really fit data that's deep just as well with the auxiliary plane for this. And it has the same ambiguity that you get with seismology. With focal mechanisms, you can't tell which is the fault plane in these beach balls and which is the auxiliary plane. That's well recognized in seismology. You can't do that unless you go to the area and actually see the fault busted at the surface. This one comes a lot nearer the surface, so we believe it's more likely to be dipping this way. When it's deep, you regain that ambiguity. Basically, your data is now in the far field, which is what seismology is. Seismology is often a far field technique unless you have measurements in the near field with strong motion. If it's too deep, InSAR becomes a far field measurement as well. If it's shallow, it's more like a near field measurement. And I did something similar here in Van. In this case, the fault propagated from deep to shallow. In the Van earthquake, we were able to understand that the slip remained really quite buried here. There's no sharp discontinuities in the InSAR data. So through the modeling, that tells you the slip is deep. So this is below 10 kilometers, and it suddenly stopped. And what would be the worry is, why has it stopped? And what does it mean for this shallower part of the fault? We can see this very clearly with InSAR. It's stopped dead here, but there's still 10 kilometers of crust that is yet to snap in this earthquake, and the city of Van is right under it. So this is a big problem for the city. So it really gives us great insight into what's going on this and the need to sort of do some mitigation in this area. So this is just an animation to really hit that home, to enable you to forward model these a bit later to understand what the depth means. If it's shallow, you've got a lot of fringes, they're very tight together. Eventually you get a discontinuity if it broke the surface. This is a profile of that deformation. You see the asymmetry, but a lot of uplift because it's reverse faulting, there's a long way around those towers, and a little bit of subsidence here. This is for 2 fault planes at depth. But you can see if it goes deeper, you've got a longer wavelength to your signal. So this is what you'll be actually doing in real time, playing about with the depth extent of this faulting. So shallow, big peak, deep, small peak, a lot more long wavelength, very narrow, very long. So that's what you're looking at. Amplitude of motion, the wavelength, and the gradient that you're looking at. And InSAR is, the reason why we, as a community, have held on to displaying these fringes for so long, and it annoys many other people in different communities, is InSAR is great at telling you gradient. Okay. So they're annoying to interpret often, but that's where the information is the gradient of the deformation that tells you a lot, which is why we keep these fringes, these contours in so much in our field. Then it was probably mentioned about the regularization, so the smoothing. So this is going back to this example from Tajikistan. We've got our multi-segmented fault. We've moved from uniform slip to distributed slips. We've broken up the fault into lots of patches. A cost of doing that is now making the inverse modeling, in this case, stable. And you have to smooth the model. This fits the data ever so slightly better, but it has ridiculous amounts of slip, 20 meters of slip on discrete patches. So you then have to do your thought process as a scientist. I've got my model, I've run it through my computer, don't believe it. Whatever you do, don't believe your models. That's the first mistake you can do with any kind of approach like this, because there's always some sort of trade-off you have to do. And in this case, it is the smoothing. And this is where the subjectivity of our work is disappointing. You can try and find objective ways to do this, and people have, but there's always a gut feeling. This is a slightly more smooth model. So now you've got 9 meters of slip as your peak. And then this is a particularly smooth model. It looks very, very smooth, in fact. But actually, it's a bit closer to what is observed as the surface displacements with different data sets from the Landsat offsets in this case. So you try and corroborate your modeling with some independent or slightly more independent data set. What do I actually get at the surface is when you press constraints. And then you just hope that there's any truth at depth, many tens of kilometers below. But you take it with a pinch of salt. And you can see to stabilize this, we've actually ended up returning from a distributed slip where we've broken up our fault plane into lots of patches, hoping to be able to solve the slip on every single one. We've actually basically returned it to just a uniform slip. So really, this earthquake is just as well modeled with just a few rectangular patches with constant slip on them. They vary along strike, but are basically the same. And we all love trying to make it look more impressive, but actually, you can do just as well with 4 or 5 fault segments, almost as well. And you have far fewer assumptions in it than you do here. And as I was saying, that smoothing and the issue with depth is displayed in this what we call the checkerboard test. If you realistically want to be able to resolve small features of that slip distribution, you'd only ever believe it in the shallowest portion of your model. You can't say I can resolve something 1 kilometer, by 1 kilometer, 20 kilometers down within InSAR. You just can't do that. You can perhaps resolve something as a slip area that's 9 kilometers large next to something that doesn't move at 20, 30 kilometers depth. But that's your sort of your resolution trade-off, because you've had to smooth your model quite a bit to get something that might be at all realistic to stabilize your solution. So again, you have to be very careful with these distributed slips and interpreting what you've done, and then when you see these papers, what has someone actually realistically been able to resolve, because it basically smears out and you get actually artifacts and edge effects and things like that. But this is often done in seismic tomographic models as well, checkerboard tests to see what they can resolve. But because InSAR's definitely measuring something at the surface, we always lose resolution with depth. So this is being able to model it with just one fault segment, that interferogram from before. Because it's deep, there's no reason to make it any more complicated than that. You can get away with one. The shallower one, though, you can see that there are 3 lobes, so you can more justifiably fit it with 3 fault segments. So you've got to do that kind of thought process. How many extra complexities do I put into my modeling? Today, with the examples, you'll just be trying to fit it with one. You'll see it does a surprisingly good job. The next level of complexity is to fit more segments, and then the next level of complexity is to bust it up into smaller distributed slips. That's the sort of methodology you would go through. So this is just the relative position then of those fault planes in this model, showing you that depth change in this case. And this is it going on to those distributed slips. That's the step. But you can see it is very blurred. It would have done just as well with a uniform slip patch, and this does very well with just 3 uniform slip patches. This is not necessarily a step you need to take, but you can see that there's definitely a cutoff where the slip doesn't occur between these 2 earthquakes. And then just to give you one final example of the motivation why we do this is an example of reverse faulting from the Zagros. This is actually radar sat at a time that we didn't really have this European Space Agency. It was after MSAT sort of died and before Sentinel was up. So if you ever go back to the archives looking for data, there are some gaps where you can't get it. You have to sometimes use commercial data that's prohibitively expensive for most things. But we wanted to study this earthquake. You see 50 centimeters of motion towards the satellite out here. This is the wrapped one. And from that, we can get at some of the distributed slip modeling to understand the depth extent of faulting. So we definitely needed 2 segments here. There are 2 distinct lobes in the deformation, so you would want that. You can see the uplift lobe, subsidence lobe, uplift lobe here are a fewer fringes, and the subsidence lobe here. And we're trying to understand then the relationship of where that slip is at depth compared to the surface geomorphology. These are these famous whaleback anticlines with salt diapirs in the middle that come up through them. How are you actually building topography? You can see an anticline here above which this slip has occurred. So this is probably contributing to the growth of the topography there. We want to understand how do you build these structures ultimately, and where does the fault project to the surface. This is a full buried slip at 5 kilometers. And you'll note here in the bigger part of the segment, it stayed below 5 kilometers and did a long thin rupture. So as I said earlier that we often used to treat these as square or equidimensional ruptures. Really, InSAR telling us that it behaves quite differently. In this case, it's a long thin lozenge of slip. Then on the other fault plane, it actually jumps up to a much shallower portion and gives you less slip, but on a really quite a narrow band here. So that's what's happened in this earthquake. And then we try and take that model on its own isn't, well, it's a bit interesting, but not interesting enough. And then relate that to the lithology in the area. So in this case, there are quite good constraints on oil wells and balanced cross-sections from the structural geologists that show that this earthquake ruptured between the Hormuz salt, which is a detachment horizon in this area where you don't seem to get the slip, that acts as a bottom barrier. And then the Kazdoumi shale horizon here that acts as a sort of top barrier. So the first event happened in the deep portion, and the along strike segment happened in the shallow portion, but it basically compartmentalizes the crust into different portions in which it can rupture, limiting, certainly in these smaller events, how big an earthquake gets before it jumps onto the next segment. And we can compare this then to the sort of patterns of incision, sort of geomorphic markers, and where the anticlines are growing, and sort of build up a sort of bigger picture rather than just saying an earthquake has happened in this area, which everyone already knows. So, as I said at the start, you're doing the for problem. We're just going to ask you to take a piece of online software and predict the displacement field given a fault segment. The much harder thing you're going to do this afternoon that's a lot slower, this is relatively easy, you'll see that it can be done on the fly even, is the inverse problem, where you've actually got a measurement and you don't know what the faulting is, but you want to know what it is. That's a lot harder problem. To solve for 9 parameters can be quite difficult if it's multi-segmented and it's really not a well-constrained problem. And there are different ways to try and combat this, but really with the Bayesian framework you've been in this afternoon, the most important thing to know is how little you know about the fault parameters. It's not just saying it's a certain strike, but it's a certain strike with quite a large uncertainty. That's the important parameter also to get out of this. You'll get a feel doing the forward modelling about how much give and take the various parameters have to fit the data. But there are formal ways of giving you a posterior density function that will tell you how poorly or how well you know a parameter. So for today's exercise, we'll be going upstairs, logging into this website. A colleague has created this online tool, uploading a lot of the earthquakes that he and others have worked on and the geodetic InSAR data set that we have for about 10 or 12 events. We'll look at 2, but please feel free to go away and have a crack at the Gorka earthquake I showed you earlier, and these other events, but we'll probably just have time to go through these 2. And just remember, you're after, the way this tool is set up, you're after the strike of the fault, dip rate, slip, how long it is, and the top and bottom depth. So that's the equivalent of the width then. You just need to say top, it doesn't necessarily have to be at the surface, top and bottom. The difference of those is your width, given your dip. And the hardest one for those who are not familiar with earthquake is understanding this rate. So that's the slip vector within the plane. So if the slip in this fault plane of the hanging wall with respect to the footwall is that way, it's 0 degrees. So that's left lateral. So if it's the other direction, it's right lateral. If it's dip, slip, normal, and down, the hanging wall is down, it's -90, which is 70. If the hanging wall moves up, that's thrust or reverse, that's +90. That's the only one that is not so intuitive. So just to hit that home, this is a beautiful fault plane from Greece. These are students for scale. Hopefully you can see in here what the rake is. It was actually covered by alluvium, but this is what would happen in each earthquake. It would slide down, giving you these grooves, these fault striations, strikes in that direction, and the rake you're measuring there. So can someone just shout out what the guesstimate of the rake would be, so I know you're roughly following? What's the rough rake?
75.
No, not 75.
-75.
Yes, minus about 50. Okay, so it's oblique normal faulting. This is, if it moved that way, that this colluvial wedge, the hanging wall sediment had moved that way, this is the hanging wall, that would have been 0, but actually it's normal, predominantly normal faulting. So yeah, it's about minus 50 or minus 60 would have been about this earthquake. So that's the only hard thing. And then your dip is measured from the horizontal down. Okay, so a normal fault is about 45 degrees. Fast fault is about -30. A steeply dipping vertical strike slip is 90 degrees. So the first one we're going to look at is actually one of the, pretty much, I think it was the first earthquake that Sentinel captured just after it was launched. It was the Napa earthquake that it just caught in 2014, the end of 2014. So it's quite a good showcase for ESA to be able to demonstrate this. Unfortunately, it was acquired in strip map mode. So that was the old sort of way. So we can't say it was the first one done in the interferometric wide swath mode. But it's the one you're going to model with, and it just showed really quite being able to have that continuous, well, these very regular acquisitions, how well we would benefit from this in intervening years, which we have done. So just to give you some context to help you out with the first one in the Napa Valley. This is San Francisco is down here. This is the Bay Area where AGU happens. Everyone often goes down here. This is the wine country up here. These are just the borders. So that's the city or the town of Napa. This is where the epicenter was, down here in the south of Napa, where people like Austin, a colleague, and some of his colleagues were looking at the surface trace, so the surface corroboration, this area. So if there's a surface trace, that tells you something about one of the parameters. Here's a DEM, LiDAR DEM for the area, showing the catchment and the mountains around it. And then this is the interferogram. Now you can see there's some complexity in these lobes. There's definitely one there, there's one there, there's a little bit there. There's coherence lost up here in the hillside. Obviously, total incoherence over the bay is expected over water. And what was great about Centaur is it can not just take the co-seismic image, but you've actually got a large number of images afterwards that highlight what's going on post-seismically. So hopefully this is the outline of Napa here as a city. Everyone can see where the fault is in this post-seismic image. This is after the earthquake. It wasn't during the earthquake. This is just purely after. There's a sharp discontinuity through here. So that shows you the fault after the earthquake is still moving. In the hours, days, and weeks after, there is still aseismic creep that you wouldn't detect seismically, most likely, but you can see in the InSAR. So that gives you really quite a good constraint on the orientation of the fault. There's the airport there. They actually had a bit of a discontinuity across in the earthquake as well, across the tarmac. So it is mainly though on one fault segment. So I'll take you upstairs now, and I'll reiterate up there that this is the online tool that we get you to log in. Hopefully you've been told you need a Google account, so set that up if you haven't got one, unless you fundamentally disagree with Google, and then just talk to a neighbor. But this is the data, okay, and this is the forward model. And this tool, it has a graphical way of giving you won't be able to see this, but these are the parameters structured from right down here at the bottom. This is a graphical way of doing it, and I'll show you on the screen. You click and drag this around to move where you think the fault is, and use all these circles to change the sort of 8 or 9 fault parameters. Top depth, the dip of the fault, the bottom depth are done by these circles. The fault end positions are done by these 2 circles. The rate is 0 to 360 or minus 180 to plus 180. And then these are the slip. This one's the slip down here. Okay, so you just literally toggle and play this, and in real time it will do the forward calculations. As I said, the forward calculation is computationally less expensive. This is a great quick tool that does that. And you can look at both the wrapped interferogram, and if you click up here on the unwrapped, and this will do the same with the model then. Once we've done it a few times, like you've had to play with this, I'll want you to tell me what you got for the fault parameters, and I'll just put them in a spreadsheet, and you'll get a feeling for what the spread of results is. And then once we've done that, you can try the L'Aquila earthquake, which was I won't tell you what kind of faulting, but it was in Italy from a few years ago, and there's an interferogram from that. So, I mean, should we just if there are any questions now, obviously we'll go through the actual online tool, but if you had any questions on mainly just the background to earthquakes, now would be a good time. Otherwise, we'll discuss the actual modelling approach upstairs for the last 35 minutes. So is there any questions prior to that then? No? That's done. It's the last day. Should we just head up then? There's no more coffee break.
Thanks, John. I did forget to mention that everyone needs a Google or Gmail account to log on. So you can set, if you don't have one, does anyone not have a Google account?